Hi again, my name is Deborah Cornelia and I'm presenting my research project, Pectoral and Elongated Dorsal Shapes, Wingtip Design and Analysis. The presentation outline are listed on the screen, and let's move on to the introduction of the project. Why did I choose the topic of the project? I'm passionate about environment, and while studying aerospace engineering, I can do some research about how to reduce carbon emission in an aircraft. Aviation industry has taken part in global warming. The carbon footprint produced by one passenger flying on a 17-hour round-trip journey, which is equivalent to heating a home in Europe for a year, 365 days. Globalization makes people travel by air more because the airplane ticket is affordable in comparison to the airplane tickets in the golden age of the air travel back in the 40s to the 60s. And fuel is one of the most expensive operation costs for the airline companies. If an aircraft can burn less fuels, it means less carbon emission as well as reduced operating costs. So it is a win-win situation for the airline companies as well as the environment. Aerodynamic improvements can help the airline companies to reduce their problem. One of the ways to increase lift and reduce drag forces are by adding winglets or shocklets in the wingtips of aircraft wings. If you sit in an airplane by the window, sometimes you can see a small device that looks like a fish fin at the edge of the aircraft wing. Winglets can reduce drag force of the wingtip vortex. This winglet idea is not a new idea. Airbus A320 has shocklet, blended winglet, and Boeing 747 has Whitcomb's winglet. So when I had to think about my own defined research project last year, one afternoon I changed my surfboard fins. I was looking at the fins and thought about how it was holding the surfboard in the water. Different fins give different feelings when riding waves. As I know that surfboard fins are based on fish fins, so I began to think about dolphins, as I often see videos of dolphins playing in the wave. Also, the white water washed look like the aircraft wingtips vortex. So I was thinking that I could do some research about wingtip or winglet shapes that inspired by dolphin fins. Hence, this biomimicry research project began. This project investigates two wingtip designs, pectoral and elongated dorsal designs, and these two designs were compared to the shocklet. The project plan that I created from the beginning of the project, it didn't change much. Starting from preliminary and then design and experimental, submission and milestone, these were completed based on the schedule. However, design and environmental phase took a little bit longer than I thought. This was because of the mesh studies as well as the wind tunnel laboratory available slot. There was some change in the data analysis and report writing phase because of the experimental results. Hence, I eliminated the fuel efficiency analysis and added ANSYS CFX for data validation. Basically, instead of reducing a task, I added more work because more steps were required in running CFD simulations. Therefore, the project planning for this research was achieved as per the initial schedule with slight change. Methodologies were required for data collection. The first method was design process, starting from choosing the airfoil to be used and creating the designs. Due to the high geometrical complexity of the design, to achieve the shape of the designs, different lengths of airfoil cords were required. And image 1 illustrates how complex was the layers of the airfoil. To create one design other than thinking about the shape, I had to think about how to get the correct measurements. The wind tunnel's working area became the reference designs. From there, I had to make sure that the dimension for all designs were equivalent to each other. When the design were completed, I printed the reference design in 3D model. Another problem appeared. The 3D printing result was not as smooth as I expected, which is showed in image 2. So to smooth the surfaces, I added UV epoxy layer resin and then I waited for the resin to harden, especially with the Welsh weather. It took a bit of time to get the sunshine. Then after the resin dried, I had to sand it down the resin to make sure that it was perfectly smooth and even to the original surface. Therefore, design process was the most challenging part of the research because of the hands-on additional works that I didn't think at the beginning of the project. The second methodology is computational fluid dynamics to find aerodynamics value of the design. Mesh studies were challenging. The original plan was to use SolidWorks flow simulation only because I'm familiar with the simulation from stress and strength analysis from the second year experiment. Apparently, the fluid dynamics simulation is different to the stress and strength simulation analysis. Therefore, when I started analyzing the data, I figured that the SolidWorks flow simulation experiment were different to the wind tunnel experiment. The idea to learn another simulation software came up. So I tried the virtual wind tunnel software, but it didn't really work. So I decided to use ANSYS CFX for data validation. The third method is the wind tunnel laboratory experiment. This method was used to validate the SolidWorks flow simulation results. This was one of the best experiments I conducted. I wanted to operate the wind tunnel machine by myself, and in this project I did, to get the results from the physical 3D model. Image 3 shows the illustration how the computational simulation domains look corresponding to the AF100 wind tunnel machine in image 4. And the image 4 shows how the physical model was tested inside the wind tunnel. However, the methodologies in this research project are inspired by the pioneering research into winglet design as well as modern engineering approaches combined. For the results of the SolidWorks flow simulation experiments, the result of coefficient of lift of all the three designs show on the left side of the screen. The curves are in line to each other with very small differentiation. On the right image show the graph of the coefficient of drag of all designs. In this graph, the proposed designs curves are lower than the reference design. Looking at the result from SolidWorks flow simulation, I thought it might be what I wanted. However, a low aspect ratio wings, fat and short, will gain more improvement using winglet, and high aspect ratio wings, skinny and long, have less drag due to the tips located in a great distance compared to low aspect ratio wings with an equivalent surface area. To verify the SolidWorks simulation results, the aspect ratio and the aspect ratio effective were calculated. The aspect ratio effective is the equation that specifically used to calculate raw estimation of wingtip due to the limited dimension of wingtip. The values can be seen in the table on the bottom of the screen. The values show the proposed design have higher aspect ratio values in comparison to the reference design, and the surface area of the old design are comparatively equal. Therefore, it confirms both proposed designs have less drag force values compared to the reference model, as well as very close coefficient of lift values to each other, because they both have high aspect ratio values. Furthermore, when designing a new wing, increasing the aspect ratio of wing is a better way to improve aerodynamics, since all designs were made using very close approximate dimensions and using exactly the same wing configuration. Therefore, it explains why the result of the three models are very close to each other and do not really show big differentiations of the results. To validate the SolidWorks flow simulation results, I compared the results with the wind tunnel experimental results of the reference design. Since the project had a very tight schedule, the CFD simulations and physical experiments were done simultaneously. The wind tunnel's coefficient of lift curve is a lot higher than SolidWorks flow simulation coefficient of lift curve. The coefficient of drag curves, both for wind tunnel and SolidWorks flow simulation, started at the same points from 0 degree to 10 degrees. However, both graphs shows discrepancies between these two methods. From the previous result slides, there are discrepancies in both experimental data results. As mentioned earlier, ANSYS CFX was used for data validation. It could be human error or machining error happened during the wind tunnel experiment. Because it was my second time using the wind tunnel machine, therefore, I run simulations on the reference design using ANSYS CFX. The results graphs show on the right screen of two CFD methods and the wind tunnel experiment. The CFX results validated the wind tunnel experiment data with CL/CD ratio accuracy between 60% to 93% around different angles. During the experiments, the wind tunnel's boundary condition as well as working area were used in the CFX configurations. The only thing that I couldn't replicate to the CFX configurations was the additional mass of the steel bar that automatically added to total weight of the 3D model during the lift force data collection in the wind tunnel experiment. This is because the lack of information of the steel bar, the total mass in relation to the length of the steel bar that inserted and glued to the 3D model's hole, plus the gap between the edge of the airfoil and the wind tunnel's wall, and then the rest of the bar length that connected to the angle of attack gauge, could not be replicated in the ANSYS CFX. What is more, both CFD results do not show the stall angles. Wing stall at high angle of attack is generated by boundary layer flow separation. The wind tunnel instruments measure the boundary layer automatically, which is opposite to ANSYS CFX software. In CFX, the boundary layer setting requires manual adjustments. To be precise, additional nodes is required around the no-slip wall boundary. This is because velocity transforms quickly next to the no-slip wall boundary, from a zero value at the wall to the free stream value a short length of the wall. Therefore, the configuration arrangements difference between ANSYS CFX and wind tunnel experiment influence the result. The results discrepancies between both CFD software because of their different meshing methods. However, both software use different base mesh. Cuboid rectangular shaped cells are different to the tetrahedral shaped cells. Also, one solid workflow simulation mesh configuration can be used for three designs as a reference mesh configuration. In contrast, the ANSYS CFX mesh methods cannot be used as a reference mesh configuration because for the thin edges in a design is required a manual adjustment in the element size number to be able to mesh the whole design properly. Therefore, this mesh sensitivity and meshing methods are resulting data discrepancies between CFD simulation results. Firstly, based on the SolidWorks flow simulation result show that both of the proposed design have higher aspect ratios in comparison to the reference design. However, one same wing configuration cannot be used to compare and measure the aerodynamic enhancement. Different designs of wingtip will provide benefit to different wing configurations. Therefore, it explains why the SolidWorks flow simulation of all designs are comparatively very similar to each other. Secondly, based on the ANSYS CFX results, to find the design recommendation, I run one simulation for each proposed designs in the ANSYS CFX at 0° angle of attack. However, the results on the right side of the screen showed that the value between SolidWorks simulation and ANSYS CFX at 0° are different to each other. It means neither of the proposed design can be selected as one of design recommendation at this point. These discrepancies due to mesh sensitivity and meshing methods as explained in the previous slides, and configuration arrangements influence the wind tunnel and CFX results discrepancies. ANSYS CFX simulation software will be used for computational fluid dynamics experiment since it gives closer results to the wind tunnel experiment. Another recommendation is various angle of attack should be used during mesh studies to find the most suitable mesh configuration instead of the lowest angle of attack or the highest angle of attack, as well as adjusting boundary layers configurations, especially around the non-slip wall boundaries, to find more accurate result as well as the stall angle. As mentioned earlier, different designs of wingtip will provide benefit to different wing configuration. Therefore, I would like to investigate further the elongated dorsal shape design using different wing configurations. So this slide is further explanation of the disruptions due to pandemic. There are so many things I would like to investigate further. Unfortunately, due to the pandemic, I cannot obtain any experiments because of the lack of access to the soft time constraint and lockdown regulations. And thank you very much.